Welcome to the presentation on the pharmacokinetics. So today I will be speaking about the membrane transport, absorption and distribution of the drugs. This class is going to be, the slides will explain about the introduction, the pharmacokinetic process, the relationship between the pharmacodynamics and pharmacokinetics, and we will also have a look at the how the biological membrane is made up of and what are the different ways the drugs adopt to get transported across the membrane. And also, if time permits, I would also like you to speak about the absorption and distribution of the drugs. So, just before we move on to the details of the pharmacokinetics, I would like to give a definition of pharmacokinetics. The pharmacokinetics is the quantitative study of drug movement in, through, and out of the body. So, as soon as the dosage is administered, so what is the quantity of the dosage and how much is getting into the blood circulation, how much is getting accumulated across the different organs and tissues, and as well as how much of it is getting excreted and what is the route of excretion. So all these can be quantifiable, and all these quantitative uh, study makes up the pharmacokinetics. So the intensity of the effect observed due to the drug is related to the concentration of the drug at the site of action, so which basically depends upon the pharmacokinetic properties. So for the drug to produce its action, it has to reach something called as a therapeutic dose. So therapeutic dose is determined uh, based upon the pharmacokinetic property, and effect that indirectly is dependent upon the concentration at which the drug is likely to produce its action. And pharmacokinetic properties of a particular drug is important to determine uh, overall dosage route of administration and at what dose, the which dose is supposed to be given, the dose is supposed to be given, and what is the onset of action. So when will the action start, and at what time you can expect the peak action time, and also how long the effect is going to last, and as well as at what interval the dosing should be given to a patient or a drug taker. So all these things uh, depends upon the all these things are part of the pharmacokinetic studies. So overall, the pharmacokinetics means what the body can do to the drug. So this slide here explains about the all those four different processes of pharmacokinetics: absorption, distribution, and within the part of the distribution is storage, and as well as biotransformation and excretion. So here is the absorption. So absorption is nothing but the drug which is presented in dosage form. So there are, all of you are aware that there are various forms of dosage forms. It could be tablet, or it could be mm, solutions, liquid dosage form, within the oral dosage form, solid and liquid, and if not, if it is a parenteral, obviously there will be no question of absorption. But if it is any oral dosage form is there, so then the picture about the absorption comes into picture. So the drug is in a dosage form, and once it is broken down by GI juices and all those things happens. So or the acid acts upon whatever happens to the stability of the drug, all those things are there. And once the drug will get released, so the drug broken down in the dosage form to it becomes a in solution form. And once the absorption is gets completed from the, for example, if it is oral dose, then from the domain of the gut it get transported into the blood vessel. So in the blood it goes. So first process is absorption. Absorption is from the dosage form up until it gets into the blood, and then once it gets into the blood, so it could be available in a free drug. And in the distribution phase, what happens is that the free drug, if it is getting attached to the plasma proteins, then it becomes the bound form, protein bound drug. And if it is protein bound drug, it is likely to be in the blood vessel only, uh, and then it reaches across along with the blood, it flows across the different parts of the body, and then at the site of action also it reaches. And if it becomes when it comes to the site of action, the bound form, if it get converted to free form, depending on the concentration gradient, so then what happens, the free drug is available to be acted upon as a side of action. Or it could be the free drug, when it is circulating to the different parts of the body, it could go and get stored in a storage tissue also. So either the two things could be happening to the free drug form. And the free drug, simultaneously it could be reaching the site of action as well as storage tissue. Along with that, it will also be going through the various excretory organs. Main excretory organ is kidney. So here, if it is going through, then the free drug, if it is there, so it could get excreted directly, or it could be undergoing the next process that's called as biotransformation. So the drug gets distributed. If it is freely available to be acted upon at a site of action, it produces action. If not, some of the drugs could be stored at a storage tissues. Otherwise, some of the free drug could be excreted out, and the majority of the drug also undergo the biotransformation. Biotransformation is done mainly by liver and enzymes, liver enzymes. So cytochrome P450 set of enzymes, so they take part in the biotransformation. And once the biotransformation is done, the main purpose of biotransformation is rendering the active drug into inactive drug. And once it is done, then either the drug, unchanged drug, or its metabolites will be next when they pass through the glomerular filtration. So there they are excreted out. If it is the route of excretion is the urine, and some of the drugs could also be excreted by bile through the fecus, and some of the drugs are capable of getting excreted by sweat and as well as saliva. So this image explains about the overall pharmacokinetic profile. So here the administration routes can be oral, percutaneous, intravenous, intramuscular, intrathecal, or inhalational. So if it is oral or rectal, the drug is likely to be put into the gut, and then from the once into the gut, it will be interchanged with the plasma in the gut, and then, as I explained, if the free drug is there, it will be producing its action. If not, it will be going through the liver also, or to circulation also, where it could be getting metabolized, and then it will be passing through the kidney, and then it could be getting eliminated. So usually intravenous, intramuscular, or parental routes, so they don't have to undergo the absorption process because the drug is directly put into the blood vessel. So as a result of that, it is directly available for the action. So, or if it is passing through the liver, then it could undergo the biotransformation as well. So route of elimination could be urine, fecus, milk, if it is a lactating mother, and sweat, and as well as some of the inhalation products, they could be excreted out via by expired air as well. So overall, the relation between the dynamic and kinetics can be explained with this flow chart. So whatever the basic reason is there, pharmacokinetics they undergo the different set of the pharmacokinetic process ADME, and then whatever left is there, that concentration of the plasma, it goes to the site of action and it produces the action. So what the body does to the drug is pharmacokinetics, and then subsequently what the drug does to the body, because it changes the physiological changes, so it causes the physiological changes, so then in that case it becomes the pharmacodynamics. So the pharmacodynamics makes up its effect. So overall, both are interdependent, dynamics and kinetics. So as I told in the beginning, so before we go into the ADV process, it is important to learn about the biological membrane and what it is made up of, and how the things are moving across the plasma membrane. If you look at the diagram, you can see that. So this is it is called as a plasma membrane, or it's made up of, it's basically lipid bilayer membrane, because you can see the hydrophilic heads projecting outside of the towards the outer face of the membrane, and the tail, which are hydrophobic in nature, so they are make up the they are inside of the plasma membrane. And on the upper side you can see the extracellular side, and the inner side you can see the below here, so you can see the cytosolic side. So this phospholipid membrane is having a different intrinsic and extrinsic proteins embedded within that. So usually this bilipid membrane is made up of cholesterol and phosphate groups, and the intrinsic membrane could be made of the pores usually. They could be aquapores or some other ion channels it could be, and extrinsic proteins, the one which has got the exposed part towards the external surface, they are extrinsic proteins, and then there could be some intrinsic proteins where the some of the proteins which are facing the cytosol, so they could be intrinsic proteins. So some of these extrinsic proteins could be acting as a receptors. So this could be some of the enzymes also here, and or they could be ion channels. They could be ligand gated or voltage gated ion channels, as well as some of them could be receptors also. So all these things make up the part of the molecular membrane. So drug, whenever the movement is need to happen, it will move across the cell membrane. So basically, the drug molecules can cross the cell membrane by some of the mechanisms such as simple passive diffusion, or it could be carrier mediated. So that is protein mediated. Within the protein mediated, it could be facilitated transport without expending any energy, or it could be purely uh, energy dependent. It could be active transport, so primary and secondary active transportation. So passive transportation is nothing but a downhill movement. It is called as. So the most important mechanism for most of the drugs. So it is basically concentration driven. It is a passive. There is no active role in it. So from the higher concentration, the lower concentration, the movement of the drug takes place. We call it downhill movement. And the measure of the drug diffuses across the membrane in the direction of concentration gradient, and there is no active role of the membrane, and it is always proportional to the lipid partition coefficient, and usually lipid soluble drugs tend to diffuse much faster across the membrane compared to the lipid insoluble drugs. So lipophilic drugs are likely have got a higher chances of crossing over the membrane compared to the hydrophilic drugs. So overall passive transportation characteristics are, so it does not require any energy, and they do not have any saturation problem, and there is no protein carriers involved. So and then not resisting the competitive inhibition. So all these things make up the passive transportation. So what are the factors which affect the passive transportation? Basically, some of the simple things such as size of molecule. So smaller the size of molecule, they are more likely to get transported. Lipid solubility, more the lipophilic the drug, it is likely to be getting crossed over. And polarity, non-polar drugs are likely to be crossing over. The degree of ionization, unionized form drugs are likely to be crossing over. And pH of the environment, such as fluid of the body, fluid in cells, blood, urine, sometimes these also determine, because basic acids, weak acids get absorbed in a acidic environment, and the weak bases get absorbed in a basic environment. So, for example, aspirin get absorbed in the gut, and then rather than uh, weak bases are likely to be getting absorbed in the intestine. So drugs which are unionized, low polarity, high lipid solubility are easy permeable through the membrane. However, on the contrary, ionized and highly polar and lower lipid solubles are difficult to permeate the membrane. So pH effect, most of the drugs are either weak acids or weak bases. So as I mentioned earlier, so if we take the example of the aspirin, which is a salicylic acid basically, so it's a weak acid, or barbituric acid, so there's also weak acid. Uh, so these weak acids or weak bases, most of the drugs are, so they will get ionized in the particular environment. The degree of ionization is determined by surrounding pH and the pKa value. So this equation, which is a Anderson-Hasselbalch equation, so gives about the effect of the pH on the drug absorption. Where pKa, here you can see the pKa is an actual logarithm of the acid dissociation constant, and ionized form A minus, if it is HA, it is an ionized form. So what are the implications of passive transportation? Gastric drugs reabsorbed are largely unionized in the stomach and absorbed faster, while basic drugs are absorbed faster in the intestine, as I told. And ion trapping is a one possibility. So where the weak acids, when they get ion trapped, so they're likely to cause the bleeding. So that's why the non-steroidal anti-inflammatory drugs likely to cause the aspirin-like drugs. So they cause the stomach ulcerations or stomach bleeding, or at least GI irritation is because of the ion trapping. And gastric drugs are excreted faster in the alkaline urine, and basic drugs are excreted faster in the acidic urine. So this phenomena or this principle is used in overdosing. If there is a overdose of the acidic drugs, then urine is made alkaline, so that the acidic drug overdosing or the toxic effect can be of the acidic drugs can be eliminated, and vice versa. So if the basic drugs are largely accumulated and they are causing a toxic effect, then the urine is acidified, so that so the basic drugs can be excreted out. Okay, this is about the filtration here. So it is passes the drugs through the aqueous pores in membranes or paracellular spaces, and lipid insoluble drugs can cross if the molecular size is small, and measure the intestinal mucosa and the RBC have small pores. Drugs cannot cross over, but capillaries which are with a large paracellular space, most of the drug can filter through this.